Hey guys, hoping all is well with everyone. So in this video we're going to be continuing with the Module 1 of the 8th grade Common Core curriculum. This is going to be section 1.3, which is ordering real numbers. So in this section, what we're trying to do is being able to compare expressions that involve irrational numbers or other types of real numbers and determine whether they're greater, less than, or equal to other expressions involving those same types of numbers. So the strategy that we're going to take here is using kind of a number line technique that allows us to estimate the value of a square root of a non-perfect square and being able to compare that with another expression with like values. And then it wants us to order a couple of numbers of real numbers from greatest to least. And then what it wants us to do after that is look at a real world story problem and be able to, again, order expressions that involve irrational numbers, non-perfect square roots, rational numbers in greatest to least fashion, and then we have another essential check-in question. So let's go ahead and jump into it. This first question, questions 1 through 8, want us to compare the two expressions with them being either less than, greater than, or equal to. So looking at number 1 here, we're going to see that for this one it's pretty easy, and the reason for that is because we see that the two square roots involved are identical on both sides of the inequality, so we can cancel those out. And because of that, it makes this one pretty simple, because now we're just comparing two integers, and because 2 is less than 3, we'll say that this one is definitely going to be less than. Actually, let me use the type tool here. This is less than. Okay. Now for this next one, we're going to start to introduce this number line method for you. So when we look at the square roots of non-perfect squares, what we want to do is kind of make a number line that compares the square root with the two square roots that are closest to it. So for example, the square root of 8 is going to be between the square root of 4 and the square root of 9. The reason that this is helpful is because we can make kind of a very good, accurate guess of the square root in question. So the square root of 4 is 2, so the square root of 9 is 3. So the square root of 8 falls between those two integers, 2 and 3. But what we can do is say this is the square root of 5, square root of 6, square root of 7, square root of 8. So the square root of 8 is 1, 2, 3, 4, 4/5 of the way to the next perfect square. So because of that, we can estimate that the square root of 8 is about 2, and 4/5 is about 0.8. So we're going to say that the estimation of the square root of 8 is about 2.8. Okay? And like I said, I want to be able to show you guys this strategy because I want you to be able to build confidence without needing a calculator to estimate at least to the first decimal place of a non-perfect square root. So one thing I want you to also keep in mind with these guided practice problems is we're using the idea of what's the principal square root. Instead of applying both the negative and positive of these values, we're just going to be looking at the positive, positive spectrum of the square root. So this is all going to be 2.8 plus 17. And then for this square root of 11, we're going to use the same strategy. So we have the two square roots that's going to be between is the square root of 9 and the square root of 16. And then we have the square root of 10 here. Square root of 11 is going to be right here. Square root of 12, 13, 14, 15, and 16. So if we look at the square root of 11, it is 2, 3, 4, 5. it's approximately 2/6 of the way towards the next perfect square. So the square root of 9 is 3, the square root of 16 is 4. So we're going to say that it's going to be 3, and 2/6 is about 1/3, or is equivalent to 1/3, so that's going to be about 0.3. So we're going to say that the square root of 3 is approximately 3.3. So again, it's using a very accurate ballpark here. So this is going to be 3.3 plus 15. So this is going to be 2.8 plus 17 is 19.8, and 3 plus 3 plus 15 is 18.3. So this number 2 is going to be greater than. Okay. Alright, let's look at the next one here. So the square root of 6 plus 5 greater than, equal to, or less than 6 plus the square root of 5. Now these are going to be pretty close, but they will make a big enough difference to where they are not equal. So the square roots of 6 and 5 both fall between the square root of 4 and the square root of 9. Square root of 5 is going to be here. Square root of 6 is going to be here. Square root of 7, square root of 8. So what we'll do is we'll do the square root of 6 first. It's going to be about 1, 2, 3, 4. It's going to be about 2/5 of the way to the next perfect square. So it's going to be 2, because the square root of 4 is 2, and the square root of 9 is 3. It's going to be 2 and 2/5. It's going to be about 2.4. Okay, so that's going to be 2.4 plus 5. And then we have 6 plus the square root of 5. So 6 plus the square root of 5 is going to be about this is about 1/5 of the way to the next perfect square. So it's going to be about 2.2. Okay, and then we can compare the two. So 2.4 plus 5 is 7.4. 6.22 is 8.2. So this is going to be less than. Okay. Alright, let's look at the next one here. So we have the square root of 9 plus 3 is greater than, equal to, or less than 9 plus the square root of 3. So the square root of 9 is a perfect square root. It's going to be 3 plus 3. And then we have 9 plus the square root of 3. So you may already notice for this one that the right side is larger than the left, because on the left is going to just be 6, and we already have 9 on the right. But let's go ahead and do the strategy for the square root of 3. It's a pretty pretty good line. It's going to be between the square root of 1 and the square root of 4. And if we look, we have the square root of 2 here and the square root of 3 here. So the square root of 3 is about 3/4 to the next perfect square. So it's going to be about 1.7. So the square root of 1 is 1, square root of 4 is 2. It's going to be about 1.7. So we have 6 on this side and then 10.7 on this side. And so this is going to be less than. Okay, let's look at the next one here. So we have the square root of 17 minus 3 is greater than, equal to, or less than -2 plus 5. So we're going to do same strategy here. So the square root of 17 is going to be between the square root of 16 and the square root of 25. And then we have the square root of 17 is about right here. So the square root of 17 is about 1/8 towards the next perfect square. So 1, 2, so 18, 19, 20, 21, 22, 23, 24, and then we have 25. So it's about 1, 2, 3, 4, 5, 6, 7, about 1/8 to the next perfect square. So this is going to be about 4.1. And then minus 3. And then the square root of 5 we saw in number 3 is going to be about 2.2. So this is negative 2 plus 2.2. Okay, so simplifying those two, we have 4 minus 1, 4.1 minus 3 is 1.1, and then negative 2 plus 5 is 0.2. So this one's going to be greater than, so 4.1 minus 3 is 1.1, 1.1 is greater than 0.2. Okay, let's look at the next one here. So we have 12 minus the square root of 2, and then we have 14 minus the square root of 8. So 12 minus the square root of 2 is about 1.4. So the two that would fall between is is the square root of 1 and the square root of 4, and it'll be about 1.4. So it'd be a little bit less than what would be like the square root of 2.5. I'm sorry. So it'd be about 1.4. So we have 12 minus 1.4, and then 14 minus the square root of 8. We saw in number 2 that that's about 2.8. So we have 12 minus 1.4 is 10.6, and then 14 minus 2.8 is 11.2. So this one is going to be that is going to be less than. Okay, so we have 10.6 and 11.2. Okay, so for this next one, we have the square root of 7, and the plus 2 is greater than, equal to, or less than the square root of 10 minus 1. So for the square root of 7, we have, it's going to get a little busy here, so it's going to be between the square root of 4 and the square root of 9. So we saw that the square root of 5 and the square root of 6, so the square root of 5 was about 2.2, the square root of 6 is about 2.4, the square root of 7 is going to be about 2.6. And we saw that the square root of 8 is 2.8, so that makes sense. So it's about 2.6 plus 2, and then the square root of 10 is going to be, I'll do it right here. So the square root of 10 is going to be between the square root of 9 and the square root of 16. And we'll see that the square root of 10 is right here. And 11, 12, 13, 14, 15, 16. So 1, 2, 3, 4, 5, 6. It's about, it's going to be about 3.1. Okay. It's going to be 3.1 minus 1. So this is going to be 2.6 plus 2, which is 4.6, and 3.1 minus 1 is going to be 2.1. So this one is going to be greater than. And then we have one last one here. But as we can actually see here, if we look really carefully, we see plus 3 and we see plus 3 again. So we can cross those out, and that makes our lives a lot easier right off the get-go. So we saw that the square root of 17 was equal to about 4.1. And then we saw that the square root of 11 was equal to 3.3 in number 2. So 4.1 is definitely greater than 3.3. Okay, so that is going to be for the first part. Again, the strategy here is to make a number line where you can determine the, first you would determine the integer or the whole number that the square root falls between the two perfect square roots, and then you can ballpark the decimal place by making that number line and seeing what fraction of the way that square root falls before the next perfect square. Okay, let's go ahead and look at number 9 here. Order the square root of 3, 2 pi, and 1.5 from least to greatest, and then graph them on the number line. Okay, so we saw that the square root of 3 is going to be equal to 1.7. So we'll go ahead and again, what we did here, like in number 4, we said that square root of 3 is about 3/4 of the way towards the square root of 4, which is the next perfect square. So it's about 1.7. Oh, I'm sorry. This is between the square root of 1 and the square root of 4. And so it's approximately 1.7. And then we can say that if pi is equal to 3.14, 2 pi is going to be equal to 2 times 3.14, which is going to be equal to 6.28. And then it wants us to put this on the number line. So we have 1.7, which will be a little bit less than halfway, but very close. So about 1.7 is right about here. We have 6.28, which is going to be a little bit greater than half between 6 and 6.5. And then we have 1.5. So if we look at from least to greatest, we have 1.5 being the smallest, or least. We have 1.7, or the square root of 3 being next. And we have 2 pi being the greatest. Okay, let's look at number 10 here. 4 people have found the perimeter of a forest using different methods. Their results are given in the table. Order their calculations from greatest to least. So the strategy here is to take all of these expressions in the form that they're in and put them into a simplified one value number, or one termed value. So what I'm going to do is because these involve irrational numbers, which means decimals are going to be involved, all of my final answers are going to be in a decimal formed value. So what we're going to do is we're going to look at each of these individually, and then we'll compare. So the square root of 17, we saw it was 4.1 for Leon, and then minus 2. So that's going to be equal to 2.1 for Leon. 1 plus pi over 2, so pi over 2 is just 3.14 divided by 2. That's going to be equal to 1.57, but let me just show you the division here really quick. So it's going to be 2 goes into 3.14, 1 times, we bring the 2, do the subtraction, 2 goes into, put the decimal here, 2 goes into 11 5 times, it's going to be 10, subtract, we got 1, bring down the 4, 2 goes into 14, 7 times. So this is going to be 1.7. So this is going to be 1 plus 1.57. So this is going to be 2.57. Okay. For Jason, we have 12 fifths. If we wanted to put that into a mixed number, it would be 2 and 2 fifths. Excuse me. So remember, to change an improper fraction to a mixed number, you see how many times the denominator can go into the numerator, and then you put your remainder as the new numerator over the original denominator. Okay, so we have 2 and 2 fifths. So to put this as a fraction, or as a decimal, we would do 2 plus the long division of 2 divided by 5. So that's going to be 2 fifths is equal to 0.4, but just to show you the division, we have 2 plus, and then 5 goes into 2 0 times. We'll put the decimal here, which will allow us to add as many zeros as we need, but we only need to put 1. So 5 goes into 24 times with 0 for remainder, So that's going to be 0.4. So it's going to be 2 plus 0.4 or 2.4. Okay. And then Ashley is already in a decimal form, which is awesome. I don't have to simplify anything with her value. So to put this in greatest to least, we have Micah with 2.57, Ashley with 2.5, we have Jason with 2.4, and we have Leon with 2.1. Okay, and that will be our answer for number 10. So again, your strategy here is to simplify and approximate or determine a decimal form of the irrational square roots or irrational expressions, and determine a decimal value, or making sure that all of the values are to some kind of equivalent, whether they're all fractions or all decimals. In this case, because it involves irrational numbers, meaning that there's going to be decimals involved because they can't be expressed as two integers in a ratio, I just went with decimal forms here. So number 11 says, explain how to order a set of real numbers. So the strategy, let me make this up. I don't want to be too wordy here, but I do want to be thorough. So the strategy is to simplify all, to approximate all irrational square roots and expressions involving irrational numbers. Then putting all the values in chronological order by simplifying any expressions by simplifying or evaluating all expressions to a single value, which then can be compared to other values. Okay, so the idea here is kind of like with number 10 here, we want to simplify all expressions to a single value by approximating with that number line technique with the irrational square roots, being able to, although pi is irrational, we can use 3.14 as an approximate value, and we can kind of see that that expression there divided by 2 was just 1.57, and then taking that rational number of 12/5 and putting it into a decimal. So we're definitely seeing at this point all of the concepts and ideas from 1.1 and 1.2 brought all together in this final section of Module 1. But I hope this helps you guys out. If you have any questions at all, again, please don't hesitate to ask. Thank you guys so much for watching, and as always, please take good care of yourselves. But I hope to see you soon, where we'll be continuing with Module 2, and we'll start to talk about exponents and the laws that revolve around them. But thank you guys so much for watching, and please take good care of yourselves. Bye.